we were looking at MultiOmics using SPLSDA to predict tumor type from gene expression data in different tumor cells. And we had done that with kind of using regularization parameter numbers that we just picked arbitrarily to determine or just to demonstrate to you how it worked. But I wanted to kind of do this last part because it brings things full circle, and because yesterday we talked about machine learning and how you use cross-validation to tune the model and choose the best hyperparameters. Well, we're going to hyperparameters being the regularization parameters. We're going to do that on this model as well. Let me share screen. There we go. So yes, that's what this next part of demo 3 is doing. And basically, the hyperparameters that we're going to use cross-validation to tune and choose the optimal value for is the number of components that are fit. And again, we can, you know, there's only so many you need to add. After a while, it's not gonna improve the classification anymore. And for the sparse partial least squares, we also tune for how many variables out of the 2000 are we going to select to have non-zero coefficients for each of the components that are in the model. And again, we obviously, if you the more of those you have, the more components and the more variables per component, the more closely you'll fit the data. But if you do too many, it'll overfit. So there's going to be a sweet spot somewhere where it fits the data well and also predicts well on new data. So what they recommend doing to determine the number of components is fit a model which has a lot of components, like go all the way up to 10, which is way more than you'll probably need. And then fit that model with cross-validation, and then look at the prediction performance under cross-validation for those many numbers for each number of components, so we can see where we eventually level off on our error rate. And you would think that the optimal number of components would be something around k-1. Like if you had two groups you were trying to distinguish from, you would need one axis to tell them apart. 3 groups would need 2. So we have 4. We're probably going to need 3 components, but you can test that empirically as well. So we're going to do this with our cross-validation, and we can, now this is how you would do it. We're going to do this first with the PLSDA, not the sparse variety, with 5-fold cross-validation repeated 10 times. This is how you would do it, but it takes some time to run. So we can just load the pre-fit model object just to show you what it looks like. So let's just go ahead and do that. So I'll go back to my our studio here, and let's see, where were we? Yes, you can. We can just skip that and go ahead and load the pre-fitted model object on line 140. That's what I would just recommend doing to save time here. Yeah, so this is the thing that I believe this will, yeah, this doesn't work, but the fix that no, this is also the problem with the previous demo. The way that you load R objects from web locations is you have to put the URL function around the name of the URL to load it. So if you could just modify this line 140 to change it to put, instead of just load parentheses, the name of the object, you want to load parentheses URL parentheses, and then close that parentheses again at the end. And that should work. So then we'll run that line. Yep, so that's what we should have done in demo 1 as well. When you have an R object that is from a web location, you have to put URL around it so that it knows it's loading it from a web location. Yes. Now we can see, okay, well, now that we've tuned our model to look at the error rate by number of components, we can take a look at that. We can see we have here is the error rate for each of the number of components up to 4, and you can see that the error rate basically is pretty high with only one component, and it goes down. But it's actually, even in cross-validation, the error rate is still declining from 3 to 4. We still have a 7% error rate for in our first cross-validation repetition on component 3, for example, and then in component 4, when we add the fourth component, the error rate drops to only 1%. For all our cross-validation repetitions, that pattern is about the same. So it does seem like adding a fourth component is worthwhile here. Yes. Oh, I believe, I'm sorry, this part I skipped. So we're actually have gone to this second part. We're not only we are not only cross-validating for the number of components to select, we're also cross-validating for the number of variables to select per component. So not just the 1 through 10 components, but also the 20 through 100 variables to retain on component 2. We're going to test how well does our model do in cross-validation with which number of components to retain is optimal, or which number of variables to retain per component is optimal for all of these across all the cross-validation folds. And we can see, okay, what is the optimal number of components to keep based on cross-validation? Let's look at that. You can see that it is determined that 3 is the optimal number of components. And what about the number of variables per component? So here are the number of variables per component that is optimal to retain. So it's 20 for component 1, 100 for component 2, and so forth. Now we can also take a look at the error rate plot, looking at the error rate for all the different number of variables per component and how many components. So we're going to plot this model object, which we call yes, optimal equals true, which tells us the which number of component variables to retain is optimal, minimizes the error rate in cross-validation. Again, balances best between underfitting and overfitting. Obviously, the more we keep, the more closer fit, but the more potential of overfitting. And we show standard deviation error bars because we did multiple cross-validation runs, just to show how variable that result was across our different cross-validation repeats. So let's do this plot. Okay, so this shows us, right, as you see, the blue line is the error rate with only one component, right? So if we only had one component, the error rate is pretty high. It was like 40 to 50%, regardless of how many variables are associated with that component. Once we add a second component, right, the error rate drops. It goes down to about 20%. There's the optimal number of variables there, 100. And then once you go down to a third, add a third component, you can see the error rate is very close to 0. And as you can see, adding a fourth component does not reduce the error rate that much more, right? Because we have enough information to distinguish between those 4 groups very reliably with only 3 with only 3 components, right? The optimal error rate is near 0 here. It's about the same. Their error bars overlap. So the adding the 4th component is kind of unnecessary and does not improve the fit anymore. It adds more parameters without improving the predictive performance of the model. So that's why 3 was shown to be the optimal, if that makes sense from this plot. So there's the plot. So yes, and that's why we have the balance between overfitting and underfitting is why sometimes you get this U-shaped pattern, right? Like too few is underfit and too many is overfit. Now, this is how you would, after doing cross-validation to tune and select the optimal number of parameters, the optimal value for the hyperparameters, what you would really want to do is validate the model externally as well by testing it on an external data set that the model building process never saw. That would say, oh, wow, we have a good predictive model. Well, we don't really have that for this example. So what we're going to do here is just do a random split between training and test. We'll randomly select 50 samples in the training set out of the 63, or randomly select 50 samples to be the training set, and the rest will be part of the test set. So that's what this is doing. It's sampling rows that we're going to use for the training set, and the other are going to be the test set. And then we're going to split our X and Y, our gene expression data, and our tumor class data into training and test. That's what this is doing. So yes, we want to sample. Sample means take a random sample of the numbers from 1 through the number of rows in X, and 50 is how many samples we want. And I set a random seed, so you all will get the same result as me. Now we'll run this block of code to create the training and test set. And then we'll check the dimensions to make sure that they are what we expect them to be. So the dimensions of the training set, 50 rows and about 2,000 columns, right? So those are the 50 samples we're going to use in the training set and all the genes. And what about the test set? It's got 13, so there's 63 total. So basically, now we're kind of cheating a little bit here because we're sort of going to not actually redo the tuning of the hyperparameters on just the training set, but really what we should have done is go back and do that entire cross-validation and tuning just on the training set. So then but we're just gonna for this example show how you would do a external validation with training and test by using parameters, regularization parameters that we already just are just coming up with, but that's not really how you would do it in practice. So we're going to fit the sparse PLS discriminant analysis to only the training set, only to those 50. We're never going to give the model those other 13 information, using 3 components and this many variables, 20, 30, and 40 per component to keep and have non-zero. We're going to use the SPLSDA function to run that, and the x.train is our training set gene expression data. Y.train is what tumor types those training set belong to. We'll run the sparse PLS on that. Now we'll take that model, those model parameters, and use them to make predictions for the test set. And so we're going to use the model fitted object, the predict function. The test set is our second argument, the data that we want to predict on. And as we show, there are different distance metrics that can be used to say cutoffs of which class each sample belongs to. They all perform similarly in what we showed before. So this is just one that you could use. You could try it with other kinds as well, like the max distance as well. So we're going to use predict function. there's our fitted model object, and x.test. So we're giving it the gene expression data from the test set. We're not telling it the groups the test set belongs to. We're getting it to predict that. So then we run that code. And what do we see? Well, let's put the a 2-column data frame where we have our predictions in one column and the right answer in the other column. Let's take a look. So here we have, for each of the 3, doing it for just 1 component, 2 components, and 3 components, and then here's the truth. Yes, Riley, do you have a question?
Yes. For the last function that we did, I got an error in predict.
Okay.
I can share my screen.
Sure, yeah, let's
Let me share my
yes,
screen.
go ahead.
Oh, there we go. Yeah, unused argument, it says.
Predict.
That's the same one I got.
Oh, I see. Yeah, I think this may be they might have, it depends. If you have an older version of R than I do, then a slightly older version of MultiOmics might be on your machine compared to mine. That yeah, I'm not sure. There could be a bug or something in your version of MultiOmics, which is odd because this worked with an older version from a year ago, and now it works with the version I have now. But so yeah, I guess Grant found a solution that you would have to use the specific predict method for MultiOmics and not just call predict in general. So it could also be if you loaded packages in a different order, then that could also cause it. Yes, so let's see. How did you do it? You had to call the predict method for that for MultiOmics specifically, right, Grant?
I put it in the chat.
Yes. Oh, I see it. Yeah.
That object has multiple, is a member of multiple classes. So maybe like the class, like the method resolution is messing up. I don't know.
Interesting. Well, yeah. So this is like
you.
One of these things that comes up when you're working with R packages that don't necessarily, you know, these are made sort of by volunteers basically. So there's sometimes bugs that make it through to when the package is deployed. But it looks like the bug was fixed in the version that I have, but we might have different versions. So I'm gonna, yes, if you run the code that Grant put in the chat, it should work. Thanks for that.
Okay, thank you.
Yeah, so I'll run that as well. It should do the same. Yeah, so I mean that should also work. Yeah, so yeah, when you look at the results, you can see that the predictions and the truth, even with only 1 component, at least for the first 6 on the test set, are all correct. It didn't make any wrong predictions, and we can make a table like a confusion matrix. We'll make a confusion matrix for this one as well to show the right and wrong on it. You can see that basically every time the truth was EWS, it predicted EWS. So in our, you know, it seems like there's a lot of information in this gene expression data that enables us to predict tumor type, and in cross-validation, at least for this very small test set, we get very good prediction performance. Now, of course, like I said, this is just internal validation. We didn't get a truly independent test set to test our model on. So, you know, you can kind of take these results with a grain of salt, I guess. But yeah, that the idea of this is just to introduce you to the sparse partial least squares. Yeah, so that's pretty much the end of demo 3. And does anyone have any questions on that? So let's do at least one more of these things while I have you all here, and if that is, you all are still interested in seeing more of these demos. Well, here, so if we only have time to do one more, let's the two that I have left, I'm not sure how long each one will take, and I do want to have some time at the end. So one is looking at differential expression analysis, like for RNA-seq data, and the other is using Diablo to kind of do this sparse least squares analysis with multiple omics data sets. Well, does anybody have a strong preference of which one they would rather do? Okay, we have one vote for Diablo. Does anybody want to go against that, or shall we just go ahead and do Diablo? All right, an overwhelming majority is of 2-0 is in favor of Diablo. So let's go ahead and do that. If we have time, we can do the other one too. But yeah, and it's also more natural. It's basically Diablo is what we just did with more than one omics together. So it kind of follows naturally from what we just did. Okay, let's go ahead and do that. Thank you, Jesse and Megan, for your input. So I will go back to the workshop page. And again, if you didn't get the worksheet yet for this demo, we're going to do demo number 5 now. If you didn't get the worksheet yet, there it is. And I'm going to open up the course materials for that lesson. So this no longer comes from the Swedish graduate course. This is actually, I kind of also lifted these materials from almost like a book of examples for mixomics. That's like a series of what they're called vignettes, our package example, our usage examples written up into a book form. You can get the full book. I have the link to it there. That's on the mixomics website. And so this is like one chapter of that. It's chapter 6. If you look it up later on. So the terminology they are using here is called N integration, which is basically just referring to any multi-omics, any situation where you have more than one omics from the same samples. They're calling it N integration. If you have different, transcriptome, genome, and so forth from the same cells, you have a multi-omics situation, and the method to use information in all of those omics together is called N integration. And so they've kind of come up with their own algorithm. Diablo is the acronym they use for it to do this approach, basically doing a sparse partial least squares predictive supervised model on multiple omics. So the example data we're going to use are from this project called the Cancer Genome Atlas Network, which again comes from tumor cells. This time it comes from, it's kind of similar to the previous example data set where we have like gene expression data from different tumor cells that come from different types of cancer. I guess in cancer biology, it's very important to be able to identify or predict the type of cancer that, so there's, we want to know, is there a signature of gene expression that can discriminate between these 3 different types of breast cancer that we have? Basal, HER2, and LUMA are the 3 kinds of breast cancer that we have. Right, and so we have here, there's going to be 150 samples in our training set that have 3 different omics collected on them: the mRNA, the miRNA expression, and protein abundance, proteome data. Now, the test set has only the gene expression data. It does not have a proteome data, but because of the way the Diablo algorithm works, we can actually predict new samples that only have a subset of the omics data in our training set. So even though the prediction set only has, or the set we're going to test our model on only has 2 omics, we can still use our Diablo model to predict what data set they belong to, or what breast cancer type they belong to. Okay, so what are we going to do? Well, we're going to import the breast cancer data as a list of 3 data frames, 1 for each omic, and these are the training data. And then we're going to take a look at how many of each cell type we have in our training data. So let's go into RStudio and open up the worksheet for lesson 3 and do that. So I'll close the one from, I'm sorry, for demo 5. We just did number 3. So I'll open up number 5. So we will load the MultiOmics package if you don't already have it loaded, and we'll import the breast cancer data. Or yeah, let me just go ahead and restart the R session just to make sure we're starting with a clean slate and there's nothing from the previous demo cluttering up our session. There we go. So I've just done that. Then I'll have to reload the MultiOmics package and import the breast cancer data set. Do that. And then I will, we're going to create this list of the 3 data frames. And you can see that I left a blank here. Data.train is one of the elements in this example data list. We have a training data and a test data. And within that data train, there's also an element called mRNA. There's one called miRNA, and there's one called protein. Those are the 3 omics data. I'm going to hit Control-Enter and run that line of code. If you want, you can look in your environment pane and press this arrow. You can see that are the dimensions of each element of X. mRNA has 150 rows and 200 columns, 150 samples, 200 genes. miRNA has 150 rows, 184 columns. I think this is kind of like an artificially small data set so that it'll run fast for demo purposes. Real gene expression data sets would probably have more than 100 or so genes, but and then our proteome has 150 rows, again, the same number of samples, and 142 columns. Okay, and if you look in your in the environment pane, you can see the breast TCGA data train has those 3 omics, and it also has a factor vector inside of it called subtype, which are the 3 different cell types we have. So we're gonna assign that to a object called Y, just so that it's easier to type in later. So hit Control-Enter there, and then we'll look at the summary of Y to see how many of each there are. You can see there's a relatively well-balanced data set. We have 30, 45, and 75 of the 3 types. So that's good for prediction. None of them are too rare. So we have a decent amount of data for all 3. Everyone good so far? Okay. Now, we're kind of going to do a similar approach to last time, where we're going to figure out what hyperparameters to use to tune our model. Once again, Diablo is kind of like a multiple sparse PLS DA, so we're going to still do like how many components and how many variables per component and everything. But there's an additional wrinkle in here, because now we have to look at the relationship between the omics. We also we have to include weights for how strongly correlated with each other the omics are. And according to the developers of this approach, there's kind of 2 ways in which you would determine that. Number one, your prior expectation of how closely correlated you expect them to be. Since we're like coming into this fairly naive, we don't really know that much about the underlying biology. Maybe we shouldn't overthink that part of it. But again, there are practical reasons as well. In this paragraph, it explains that you can if you set the weights of how highly correlated you expect the different omics to be very high, that will be better for prediction, but it will not be as good for classification, and vice versa. The small weights will be better for prediction. So yes, basically, it's kind of like the same idea with regularization, like how close you want to fit the data versus how well you want to predict the out of sample. And so I think the lower the weights are, the less closely it'll fit the data, but the better you would expect performance on the test data. And so that's why the weights can kind of go up to 1. And so they've chosen 0.1. Again, in reality, you would probably want to test this or cross-validate with different weights and then see which one had the best out-of-sample prediction performance. But we're just going to use 0.1 for all the values in this design matrix, which are like the correlation weight between mRNA and miRNA is there. So that's how we're going to do that. 0.1 we're going to put in for all those values. Hopefully that makes sense to everyone. So yeah, we're going to put 0.1 in for all the values of this design matrix. But the design matrix has to have 0 on the diagonal. So we're going to say diag of design gets the value of 0. If we run these two lines, and then we print the design matrix, you can see it has 0.1 everywhere except the diagonal. So we're kind of just like manually choosing regularization parameters here instead of doing cross-validation for those particular parameters. Okay. But there's still those, even though we've set the weights fairly low, they're still non-zero. So we're still allowing the model to find correlations between the omics that are associated with the outcome, the tumor type, if they exist. Another option they also say for looking at the correlations between the data sets is to do separate PLSs on separate PLS analysis on each pair of omics. Since we have 3, there's 3 pair combinations with just one component. And look at the cross correlations between the components associated with one omic and the components associated with the other. And those could be used as weights in your design matrix. So this option is another way to do it. If we had time, we could like play with this a little bit more, but I'm just gonna I'm just gonna just show you real quick. So we'll PLS, not a PLS discriminant analysis, a plain partial least squares analysis with only one component. So we're doing that for each combination of each pair of omics. We did it for mRNA and protein, mRNA and miRNA, and we're doing it for protein and miRNA. And each time we're going to use the COR, the core function, to look at the correlation between the components for one omic and the components for the other. So if we run all that, those are our, you can see they're highly correlated. They're like 0.9, 0.8 or so. So according to the developers of this algorithm, you could actually set your correlation weights as high as 0.8 or 0.9 based on this sort of pre-analysis step. But again, if prediction is our goal, we can kind of choose whatever we can. Right. If this is sort of a more machine learning approach, what we really care about is prediction. So we can turn the knobs and twiddle the dials, dial in exactly whatever gives us the best performance is what we want. Like, it doesn't really, it's up to us and our goals of prediction of how we set those hyperparameters. So you can kind of do whatever works best. We can let the results speak for themselves. Okay. Now, just like we did in the previous demo, right? We wanted to know how many components we should use for our PLS analysis. Well, the way we did that was fit a model with a lot of components, and then use cross validation to determine what number of components give us the best error rate. And so that's what we're going to do here. Basically, this block PLSDA, that is the function that actually runs Diablo. Diablo is a form of, they call it block PLSDA, block being the different omics. I don't know why they call it block, but yeah, that's the function that's actually doing the Diablo analysis. So we're going to do this Diablo on our X, that is our three different omics, the two different RNA expression in the proteome data set. Y is the vector of what tumor class the cells belong to. We're going to use 5 components, and we're going to use this design matrix the one that has 0.1 for the correlation weights. Now, we're not doing a sparse PLSDA, right? We're not selecting how many variables per component to retain. We're just using them all. And so there's no sparse aspect to it, so that we don't have to do that keep X parameter. We're just doing the number of components and the weights of correlations between the omics are the two hyperparameters we're using. So we're actually going to run a Diablo model right now that way. So it's block.plsda is the function. X is our gene expression for our RNA-seq and proteome list. Y is the number, or is the factor of cell types. Number of components, 5, and design, and we called that matrix design as well. So design equals design. So now we'll run that line. It'll run our Diablo model with 5 axes components. Okay, so that gives us some sort of note, but everything seems to have worked. Now we're going to do our 10-fold cross-validation with 10 repetitions to figure out how many components is optimal. And we set a random seed, right? Because cross-validation involves random splits between the blocks. So how will we do that? We're going to use the perf function for assessing model performance on this Diablo object. We're going to use m-fold, so that's telling it to do cross-validation, 10 folds repeated 10 times. Of course, you could repeat it more than 10 times. It's just a matter of how much, the more the better. It's just a matter of how much time you want the computer to run for. We're going to use the perf function. The validation argument tells us that we're going to do cross-validation to assess the performance. 10-fold, which is usually a good rule of thumb to use, and repeat 10 times. Hit Control Enter. Oh, well, we'll run that whole thing, including the setting of the random seed. Highlight that and then hit Control Enter. So we're basically fitting this model 100 times, so it's going to take a minute or so to run. And then after it runs, we're going to look at the error rate and as printing them to our console and also looking at a plot of the error rate. So yeah, it just got done running, so it shouldn't take too long. So first, we're going to run line 41 to list our error rates. So yeah, you can see we get a bunch of numbers, right? Because we have 3 different omics. there's 3 different distance metrics that can be used to generate a prediction, and we have 5 components. So yeah, we won't go through it here. It's easier to look at on a plot. So let's run the next line, which will make a plot. So we can see that here the different colors are the 3 different distance metrics, and the solid line is the balanced error rate, accounting for the imbalance in the number of samples we have of each tumor type, and the dashed line is just the raw error rate. So you can see, okay, what do we see here? Well, it looks like one component isn't very good. It has a pretty high error rate. Once you get to 2 components, the error rate goes down to 5 to 10%, depending on the distance metric you use, and it never improves after that. Looks like that makes sense because we got three tumor types, so really 2 components should be plenty to distinguish between 3 categories. You usually need 1 less components than the number of categories you have. So it should not be surprising at all that 2 is adding more than 2 does not benefit you. So 2 seems like the way to go. And also we see that the centroid and Mahalanobis distance are a little better performing than the max distance metric. So we can just pick the one that does best for us. Yes, and so we can draw our conclusion that 2 components with centroid distance metric is what we want to go with in our final model. And you can also take a look at the optimal number of components according to the prediction distance and the type of error rate, if it's the overall rate or the balanced error rate. So actually, yes, as it turns out, even though to me it looks like in this graph that 2 is just as good as 3, it does seem like the error rate dips a little bit lower when you get to 3, because if you run this line 48, you can see that regardless of the error balance versus raw error rate, and regardless of the max of which distance metric is used, 3 is maybe a tiny bit better than 2. So it's like, well, we may as well use 3 components, not 2, since it does give us a slightly better. We're wrong a little bit less often with 3 components than 2. And so, again, this next line is just like saying, okay, out of this matrix, we're going to use the optimal number of components selected based on the balance error rate and based on the centroid distance. Well, all this is going to do is give us a 3. This is just going to give us a 3. Because all the 3 was the optimal number of components regardless. So if I run that line, you can see in our environment, NComp is 3. Okay, so now we are going to do a sparse. We've basically used our simpler, not sparse version to select that 3 is the optimal number of components. Now our next step, we're going to do a sparse PLS Diablo, where we actually are going to do that regularization and select only a fewer number of variables from each of our omics to have non-zero coefficients in the final model. So right now, instead of block PLSDA, it's SPLSDA. And we're using tune block SPLSDA to do cross-validation again. And yeah, just in the interest of time, we are only going to repeat the cross-validation once. We're only going to fit, since we have to fit a lot of combinations 10 times, we're only going to do 1 repetition. In reality, if you were doing this for a publication or in reality for real-world application, you would use more than 1 repetition. But this will only take a minute or 2. But you have more time if you're going for a pub, so you would increase the number of repetitions to a higher number to where you get a more stable converge on a stable answer. So what we're doing is we're going to test a bunch of different combinations of how many variables per component to keep. Now we're going to we're going to do basically first do it by ones and then a wider spacing. So 5, 6, 7, 8, 9, 10, 15, 20, 25. And they recommend not going too much lower than 5 because you do want to have it's possible that many of the variables in our omics are going to be correlated with each other, but we do want to have a biological interpretation for the results. So if the data sets are sort of almost too easy to separate with too few variables, we'll just like kind of get a couple of genes that almost selected at random to out of the correlated variables to predict. And if we don't go down too low, then we'll have we'll be guaranteed to get at least a decent number of at least 5 genes from each of our and proteins from each of our omics that are selected in our final model. That's why they don't go all the way down to 1 or anything like that. So right, so this is just telling how many of each. We're testing all these different numbers of variables to keep as our regularization parameters for our sparse PLS. Then we're going to do this with, well, yeah, I guess in this code we're using 2 components, even though 3 was a little bit better than 2. We're just going to use 2 since it was about as good. And we're going to test out these different values of how many variables to keep, use our same design matrix and 10-fold cross-validation repeated once. And we're going to use the centroid distance error rate because it was shown to be the one with the centroid distance to determine the predictions because it had the lowest error rate. So we're going to use the tune lock SPLSDA function. And we're going to use 2 components, ncomp equals 2. We're going to use 10-fold cross-validation, repeated 1 time. Use this grid of keep x values we just talked about, and we're going to use centroid distance as our distance metric. And again, I'm setting a random seed, so you'll get the same numbers as me if you do it the same, if your code is identical to mine. So I'm going to hit Control Enter and run that. And yeah, it tells us, okay, we did 9 different numbers of 9 different possible numbers of variables to retain for one of the omics, 11 for the other, and 5 for the other, 5, 10, 15, 20, 25. So it's doing every possible combination of that, right? 9 times 11 times 5. It is fitting the model 495 times, and it is doing 10-fold cross-validation, right? So it's actually fitting the thing almost 5,000 times, right? That's why we're only doing 1 repetition because as we're sitting here talking, that's going to take a decent amount of time. Obviously, if you, I think it only takes a minute or 2, but if you were doing this again in a real world application, you would do even more than that. Since, you know, the SciNet cluster can be used to run these kind of things in parallel. There's options you can set on this that will automatically run the cross-validation folds and the different combinations in parallel over multiple processors on your machine. If you have a laptop with a lot of cores, or if you're running this on the computing cluster, you would have to set those options to run it in parallel, and then it would use more computer chips basically going at the same time to run the thing all at once. And it would be quite a bit faster. But I didn't bother with that for this because it only takes a minute or 2. While it's running, we'll take a look at what are we going to do. We're going to, after it runs, we're going to pull out what it selected as the optimal number of variables to retain from each omic. And then we're going to use that in our final model. And after that, the rest of this demo is basically looking at some interesting plots and other outputs that you can make from a Diablo analysis that actually, you all, some people in your research group have done this. Lakshmi sent me a paper you did that had, from your group, that had a lot of these, that some of your external collaborators did a Diablo analysis on some of your data that was included in that paper, and included a lot of the plots that we're going to show. So hence why I thought it was interesting and useful for me to go over exactly how they did that, so that you can not have to pay them to do that analysis next time and cut them out and do it yourself. Much to their dismay, I'm sure. Okay, so yes, now we can look at this choice. Keep X is what was selected to be the optimal number of variables to retain per omic. List.keepX. We can look at it if I just type the name of it in the console and hit enter. You can see that here are since there's two components in here, it has two numbers for each of the three omics. So basically, the cross-validation told us that it's optimal to keep 8 variables from the mRNA expression data set for the first component and 20 for the second, and so forth. That's what this is. That's what that long cross-validation of fitting 5,000 models. The whole point of that was to come up with these numbers. Okay. Now we've tuned our hyperparameters. We can fit a final model using those hyperparameters we chose. And we don't have to use tune block SPLSDA anymore. We can use block SPLSDA to fit our final model. And we use our same design matrix, because we didn't cross-validate to determine that. We just set it. We set it by manually. Use our block. Right, block SPLSDA. Keep X is our list dot keep X. I'm going to run this these lines of code now. And it says design matrix has changed to include Y. Each block will be linked to Y. And so if you run, if we want to look at what the design matrix looks like now, I'll hit Control Enter to look at that. You can see that it has our 0.1 weights that we came up with before, but it also includes a weight of 1 for each of the omics with Y. So we're saying that we want to estimate relationships between each of the omics and our outcome, our tumor cell type as well. It does that automatically for you. We're looking at relationships between the omics and the group variable. Everyone following? If anyone has any questions or is stuck, let me know. Okay. We can look at the which variables, like which, if you actually cared, which of the loci, which of the genes in the mRNA expression data set were the ones that were selected in the final model for the first component. We can use select var to look at those. Let's do that real quick. Select var. Right. So yeah, these are the names of the of those genes. And they note here, if you remember, we did this stability analysis where we looked at which variables were most consistently selected across the different cross-validation folds. But we can't really do that here because we only did one repetition. But you could do that the same way as we did for the PLSDA previously. And there's a function now. Oh yeah, now we're basically going to gonna do a bunch of plots to take a look at what pretty pictures we can draw from this analysis we just did that will be informative visualizations that could go in a manuscript and help people see patterns in your data, and you can tell biological stories about them. That's kind of the rest of the demo here, which I'll cover for the next few minutes, and then probably at that point we can do office hours if anyone still wants to stick around for it. Plot Diablo is one of them, and we can look at which component. You have to specify which component you're going to look at, and it will show you the correlations between the components from each of the 3 omics. And so we're going to run that on component number 1. Plot Diablo. And comp equals 1. I think the numbers are slightly different than what is in the notebook because I'm not sure why. Maybe the random seed got reset to something different. So you can see it shows the pairwise correlations are very high between the components associated with the different omics, and also this shows the location of the samples from each of the 3 omics plotted, each pair of them. You can see that the separation between the 3 omics, because the points are colored by the tumor type. And the ellipses around them are the 95% confidence ellipse for that subtype. So if they don't overlap very much, you can see that they are the difference between them. Yes, Bharat, question.
So the question is like, so that's the correlation between the components which are coming from the principal component 1, right?
That's right. So these are the correlations between the first component extracted from the miRNA dataset and the first component from the protein dataset are positively correlated, like with a correlation coefficient of about 0.8.
Okay.
Yes, and so that's showing the those sort of like there are at least some genes that are highly expressed with the same samples that some proteins are very highly expressed on. So there's correlation between them in that way. And that correlation is associated with, it's also associated with subtype, right? Like there's, this particular type of cancer cell has certain genes that it highly expresses and certain proteins that are highly abundant in that cell type. So there's association both between the different omics and that is associated with a particular group in the data set.
Follow-up question.
Yeah.
So the list of can we know the list of the genes which are driving these correlations? Do you think that list of genes also represents the loading weight, in the loading plots?
Yes, it should, right? The ones that have the, yes. That's what we see. These are like the loadings. You can see the values. These are the loadings on that first component when we did select var. So these 8 genes in the mRNA data set were selected, and they have most of them have a positive loading, one has a negative, and so that it looks like the mRNA, the ones with a positive loading, are associated more with this LUMA cancer type, right? Because that is the one that's on the positive end of the axis there. Does that make sense?
Yeah. Thank you.
Okay, and now we can also do plots where we look at 2 components at a time, usually the first and second component, and we can plot each sample, each of our 150 samples that we have into the first 2 components from each of the omics, and you can do that for all 3 omics at once. And you could put confidence ellipses around these if you want to. So we're going to do that for all 3 omics at once here with the plot indiv or plot individual function. And so when we look at it, you can see that that's how well all 3 of the omics are doing reasonably well at separating the samples. Although the miRNA, there's maybe more overlap here. They're not perfectly separated. Some blue ones are way over here, but the mRNA seems to have a stronger signature distinguishing the cell types here. That's what that'll show you. And there's various options you can customize that plot with. And this plot is kind of interesting. It's a little busy, but it may also be useful for you. Basically, this shows this arrow plot takes each sample and plots a centroid and then puts 3 arrows sticking out of it, 1 for each of the omics, showing the distance between the centroid for that sample across all 3 of the omics and the location of that centroid of that sample in the first 2 PCA axes for each omic separately. If the arrows are really short, that means all 3 of the omics have very close agreement with one another and classify the samples in the same way. If the arrows are long, there's a lot of disagreement. The plot arrow is doing that. Plot arrow. Example of another plot you can make from a Diablo analysis. Here we see, so even though there's some overlap, there's most of each you can distinctly see the 3 clusters of cell types there. So even though some of them overlap, there's pretty close agreement. So each omic is classifying the samples in more or less the same way. Especially the gray ones. That's the one that was most strongly associated with the first axis. So these ones have shorter arrows, it looks like. Yes, Bharat.
I have one more question. So
Yeah,
I'm assuming that each point is coming from each sample, right?
Yes, there should be 150 points on here. Well, there's 150 times 4 points on there, 1 for the center and 1 for each of the 3 omics. So there's, each sample has like a Y-shaped, because in this particular data set, we have 3 omics. So each sample is being classified overall and separately by each of the 3 omics. So there's 4 points for each sample there.
Okay, so in our paper, which we published, so I had a question regarding that. So when we are done for the blocking, right, and we didn't use the centroid, we just blocked with the variables.
Okay.
So in some cases, the number of points were decreased. Basically, if we started with the 10 samples. And we see the plots with 4 in one section, like,
I see. Well, maybe there was some missing data. Like some samples only had some of the omics or something?
But the thing is, like, when we block, for example, take mRNA, right? Like when we block with mRNA, I see like 10 samples. But when we block with protein, I see the samples like maybe 4. Like it's not, there is no equal number of samples.
Okay. Yeah, I don't know. Well, I'll have to look at that paper again because I don't remember that. I don't know why that would be the case unless some of the samples did not have proteome data for them.
Yeah, but we at the end, I think we excluded to include in the data like regarding that. But like I had a question, right? Like how do the sample number decreases, right? Like
Yeah, I don't really know the answer to that right now, but if you show me the plots later, I can maybe try to figure it out.
Okay.
Sorry.
Yeah. Thank you.
Let's see what's next. Well, there's a few other types of plots we can make. Again, these are all just different ways of visualizing the results. We kind of have an overall story, and you wouldn't want to put every single one of these plots in a manuscript, I wouldn't think, because it would just like overload the reader with information. But you could kind of select the ones that you think illustrate the story the best, because they're all just different types of visualization that can be made from this Diablo analysis. Plot var, that's a correlation circle plot, like this donut plot, like we made in the previous demo from our sparse TLS. We can also do this for Diablo. There's a bunch of options on here that I won't get into, but we'll take a look at the plot and see what it's telling us. Plot var is the name of the function. Run that. Okay, you can see there's each of these. Let me see. What does the legend say? So yeah, each of the each dot here is actually a variable. So it is a one of the genes or one of the proteins from each of the 3 omics data, and the different symbols are the 3 different omics that they come from. So we can see in here that in component 1 of our Diablo, there's like a bunch of mRNAs and a bunch of proteins that are highly positively associated with that and with each other, right? Because if they're not as many miRNAs, but some miRNAs have a negative association. They're less highly expressed in samples that have a high value of component 1. It's the ones that are like near the positive or negative 1 that are the most associated. Now, obviously, if you wanted to, you could actually label this plot with what genes those are, which might be more informative. So, that would be something you could do to actually see which protein is it that's so highly positively associated with component 2. Now, another plot that you had in your manuscript is a Circos plot, which you can also make from Diablo. It's a very complicated plot, which I think, to me, is almost too busy and hard, difficult to interpret unless you do a really good job explaining in the legend exactly what the heck this plot even means. But you did have it in your manuscript, so I felt like it was important to show here as well. Yes, we have basically there's a bunch of different options for the Circos plot, but the main thing here is it's going to show there's sort of 3 sections of it for the 3 omics, and then there's lines going through the middle that are showing positive or negative correlations between any 2 genes or proteins in the different omics data. And red, or like those sort of orangish lines, are positive, and the black or gray lines are negative correlations. And then around the outside, we also see these show how highly expressed or how much protein in each of the genes and proteins there are in each of those cell types. So like, this mRNA was highly expressed in the Loom A cell type, right? Because it's higher value of the gray line than the blue line, for example. So you can use Diablo to make Circos plots like this. Right, and so the color blocks, this shows what color the 3 different omics are going to be colored by, and the color core is the color for the positive and the negative correlation. So the chocolate is like that orangish brown color for the positive and the gray for the negative. Color the blocks, the different ohms, and color the correlation lines. And it's only showing correlations greater than positive or negative 0.7. You could obviously set that to a different cutoff if you wanted to. So that's Circos plot. Cutoff equals 0.7. Again, you could use a different number if you wanted. Color dot blocks to color the omics, different colors. And color dot core to color the correlation lines, different colors for positive and negative. And you can see we've generated the Circos plot. Again, I think I didn't set the random seed maybe to the same as last time, so these numbers are slightly different than what we got last time, which is it looks a little bit different than the plot in the notebook, which is not a great sign, I think. If the if changing the random seed a little bit gives you a totally different result, that's kind of a bad sign for the sort of overall validity of these results. But again, this is a very small example data set with not too many samples. Yeah, I think there's a few other, I'll just kind of skip over this network plot here, since I don't think it's too relevant. The other thing you can do is plot the loading. So like we can actually, I think Bharat asked about this as well. We can look at for each of the omics which particular genes or which particular proteins are highly associated with each of those components and which cell type are they predicting the most strongly. And so we can do this for the for component 1 for the ones that the color indicates the class in which the variable has the maximum level of expression, either the mean or the median of that. So let's take a look at those loading plots. I'll skip the network part. Plot loadings. We'll do component 1, maximum contribution, and the median. And so you can see that we have a number of yes, this is giving slightly different results than the notebook that I have, but basically here's for mRNA, we showed that some genes are highly expressed in this gray cell type. For miRNA, some have very low expression in the blue cell type, and then there's protein differences as well. So that's what those loading plots are showing you, right? So these are like the genes and proteins that are most associated with differences between the cell types across all 3 of the omics. Kind of useful thing to look at. And so those might have a biological interpretation. Maybe they're part of some related pathways and things like that that you could look up. You can also do a heat map plot called CIM, clustered image map, and this this is kind of a 2-way heat map, looking at on one side the groups, the cell types, and on the other side the different omics, and we can look at which ones have sort of high positive associations and high negative associations, again with each combination of cell type and omic that it comes from. So we're going to use the again, we're going to use component 1 for this. You could plot it for the other components as well. CIM Diablo for the heat map. We're going to run this code here. Let's zoom in and take a look and try to interpret. I'm not sure if you had this type of plot in your manuscript or not. Basically, you can see that here right, so the red is the miRNA, and so it says, well, here are in this blue cell type there was some miRNAs that had a high expression, and that was associated with component 1. And so it seems like component 1, and then these different mRNAs and proteins had high expression, mostly in the gray cell type. So component 1 is associating with that as well. Those are kind of the two main patterns that stick out. It's like these particular, and you can see the names of the mRNAs and proteins here. These particular mRNAs and proteins have high expression in the gray cell type, more so than in the other cell types, and these particular mostly RNAs and some proteins have high abundance in the blue cell type. Maybe there's a story to be told there. Now we can also do our 10-fold cross-validation repeated 10 times, not to tune the parameters anymore, but now to look at how good prediction performance it does. We're going to do the take our final model and kind of refit it to different subsets of the data, right? A different subset until all models have been predicted, and then see how well it does overall. And we're going to use that centroid distance because that was what we determined had the lowest error rate. And we're going to do 10-fold cross-validation 10 times. Again, because Diablo is kind of like a predictive model, we can do that. We're going to use 10 folds. Going to repeat it 10 times, and we're going to use centroid's distance. And again, we're going to set the random seed. Presumably, we should all get similar results, but it seems like there's some inconsistency between some of the versions. But this will take a minute to run, and we're going to look at the there's two different error rates: the majority vote, that's kind of like the raw error rate, and then the balanced or weighted error rate. And so what do we see? Let's run this majority vote error rate line. You can see that these are the percent or the proportion of the time that we got a wrong prediction on the data points that were not used to fit the model. You can see that it kind of is overall lowest with 2 components, and then it goes up again with 3 components, right? Like there's 8% error rate, then 5%, then back up to 13. So that's where we see the overfitting coming into play. 3 components is overfit. It's fitting too closely. It's fitting random noise in the data. Seems like 2 components is really best, if that makes sense. And the weighted vote error rate gives a very similar interpretation. It's better with 2 components than 3 because we don't want to overfit. Okay, nearing the end here. There are other things you can do with that prediction, but we'll another plot you can make to assess prediction performance is an AUC plot. If you ever do machine learning applications, you will probably see a plot like this. Basically, it's showing where we get the best balance between minimizing both the false positives and the false negatives. If your model falls exactly on this diagonal line, you are doing no better than random guesses. You have a terrible model. The best you want is to go straight up and then flat across the top. So the closer you are to this upper left-hand corner, the better, and in an area under the curve plot. We can look at this for any of the omics. AUROC, area under the receiver operator curve. And we can do this for any of the blocks. We'll just do this one miRNA and the first component. So here, this looks a little bit different, unfortunately, than the output from the in the notebook. But you can see that Yes, using component 1 only, we're doing a very good job identifying the basal and the LUM A tumor types, but we're doing pretty much no better than random guessing for the third one. And if we did component 2, I think we should see that it's also that's the one that's pulling out that third cell type. Yeah, so if we add a second component, you can see we do a much better, and it's also doing a decent job predicting the third cell type as well, because we kind of need two axes of variation to distinguish between 3 groups. Okay, so let me just, I guess we might as well, get your money's worth and finish up this this lesson, and then we'll kind of adjourn for the day. We can also, if you remember, a long time ago at the beginning of this, we had a training set with 150 samples with 3 omics. We also have a test set that only has 2 omics with a smaller number of samples, which is actually nice because we have a sort of semi-independent validation set to see how well this Diablo model we fit does on predicting a whole new, predicting the cell types from a whole new external data set. So we're going to make a list of, we only have the 2 omics, right? We don't have the proteome. We only have 2 RNA expression data sets from the test set. We're going to put them together in a list, and we're going to do the predict. We're going to run predict on that. We're going to, yes, so we'll create this list of data. We'll run predict. And our new data is going to be this list of test data with the 2 omics in it. We'll run that. It gives us a warning that some of the omics are missing in the test set, but obviously we knew that already. So the last thing we're going to do is make a confusion matrix and see how often we were right and how often we were wrong on this test set. Get confusion matrix is the function we're going to use. Truth is the actual tumor types that we know from the test set, and predicted is the what our Diablo model guessed they were. And let's see how often they match up. So this is truth and predicted are the 2 names, and get confusion matrix is the name of the function. Get.confusion matrix. 2 arguments are truth and predicted. Run that, and then let's look at the confusion matrix. We actually did quite well, right? Most of the positive highest numbers are on the diagonal. We were only wrong a few times. When it was basal, it predicted basal 20 times and only predicted one of the other ones 1 time, for example. So yeah, I would say, depending on what your needs are, that's actually a reasonably good prediction performance. And we can get the balanced error rate. So this is like the adjusting for the non-balanced nature of the test set. We can get a overall error rate. Get.ber for the balance error rate from the confusion matrix. So it's about, well, in this particular run, we got about 6%. Okay, so yeah, that's the end of demo number 5. Does anyone have any questions on that? Now that we've made it through that long set of examples? Okay, well, I'm going to stop recording now. Thank you again.